to be able to achieve the score of 8192. So far what has been done is this is like the sample game logic for 2048, the game, and I can refer to the previous videos for what it does. So firstly, I created a random AI where it basically just like starts with this like the game state, and then through a series of random moves, it reaches this state here. And finally, we have a Monte Carlo AI, which basically evaluates for like maybe 100 tries and then goes to a depth of 10. Okay, this will take a while, so I'll just like maybe do 20 tries instead. So this will basically just take in 20 different, so they will evaluate the first move, like let's say for example up, down, left or right within the valid moves. It evaluates the first move, and then it will do like 20 random simulations where they do random rollouts. Basically it just plays a random move all the way until it dies or game's over, or reaches the max step, and then it chooses the move with the best one. So let's just see. I just did 20 because I just want a more fast paced game because I would like to focus on the Monte Carlo tree search based AI. It's not a real Monte Carlo tree search because to do that for like maybe 100 tries only is not exactly that great, because like if we were to do only 100 tries for this Monte Carlo tree search, it may not actually do give a very good score actually, uh, because of the limited number of simulations. There's like four moves per depth of the tree. The tree can go up to maybe 1000 depth, and so that's like all the above 1000. That's a 600 over a number with more than 600 digits. Oh wow, with 20 tries it can go so far already. So actually this 2048, this core game itself isn't that tricky to implement, I guess. So maybe if I have like a random four break sometimes instead of just having two. Oh wow, look at that. I think this will end at 4096, judging by how it's going. Yeah, it seems to be going pretty fast. So yeah, seems to be going pretty fast. Yeah, so I just wonder like if we were to do an explore exploit kind of constraint in this, whether this would actually work out. Yeah, then I actually also would like to implement the thing called deep queue networks. So I'll probably stream it next time. Yeah, it might take a while because like the DQN may not work straight away. But yeah, DQN is using a neural network based approach in order to do this kind of single player game. And yeah, so actually all this like multi-arm bandit, dynamic programming, Monte Carlo, temporal difference, all these are very useful game concepts. Yeah, so deep queue network just uses the previous state and then learns from it, and then you just keep doing the bootstrapping for this, and actually it works surprisingly well actually to just minimize the prediction error. Just like that, it can work very well. So if we were to encode the bot state as a neural network, we minimize the prediction score. That would be quite good already. Okay, it's not too bad. It ended off at 2048. Okay, and there's 1024 already. So a score of 32844 for just the simple Monte Carlo AI method. Okay, so now I think the playthrough function, I can keep it. Let's just copy and paste this thing here. Now we'll be doing something called what I'll call Monte Carlo with exploit. I mean, ideally we would like to do like a full um, ideally we'd like to do a full kind of Monte Carlo tree search method. Monte Carlo tree search, for those who don't know, let me just show you what it is. So Monte Carlo tree search, you have like a certain graph like that. You will randomly select, like let's say for player one, you will randomly select a node here. Let me zoom in a bit. You will randomly select a node here based on the explore exploit constraint. So basically, you have this term called the exploit term, which is basically based on your win rate. So like let's say if this branch leads to a higher win rate than the other two branches, each branch corresponds to an action for the game tree. So like let's say over here is the the action up, then here's action down, here's the action right, and so on. So each branch corresponds to the, so basically the you will choose the branch that has the highest exploit trade off. And how you calculate that, for the exploit you just take the number of like percentage of wins as the value, and then for the explore you typically use like a constant typically is like 1 times the square root of the number of times you haven't visited that state. So it's normally over here. Win rate plus constant times square root. Ln NI means the number of like times you have selected this node. And then the bottom one is over the total number of simulations for that node. Okay, so we'll do something like this. So like the more times we visit a particular node, the less likely we want to visit that node again. So this basically tries to trade off, uh, like it tries to, so we have a few actions we can choose for the first move. We try to choose the action based on like its final value over here, okay, plus a constant term here, which would be indicative of like how long we haven't explored that branch. So the longer you haven't explored that branch, the higher this term would be. Okay, so let's just do something like that. So let's try 20. Okay, and then for here, so it should be it should be like 80 right now, because like we, okay, I keep it as 20 first. So 20 times 4, because now we can do all 4 actions. So over here, if valid moves dot append move. So we do have a valid move array here, and then we can do here for to- total tries in range num tries. Okay, so we have a total tries, and then we would like to have the, so node tries or action tries. Action tries will basically be like the number of times we have tried this action. So we initialize it to be an all zero matrix at the beginning. Okay, and then what we'll do here is we will perform and explore exploit trade-off calculation to find out which move to go first. Okay, perform Monte Carlo simulation for that move. Okay, and then after that, actually there's no need to do it after that. So we do have an action tries here. We do need to have a score for each of the moves. So what we do is we will have a score. We will have a score for each action. So action score, we have it to be a zero matrix like that. So every time we update the score and action. So over here, the new use, okay, we call it explore exploit. Okay, why not we just call it like the action heuristic. Okay, the heuristic for that will be the, okay, let's just take a look at how it's done. Win rate divided by n. So the win rate will be given by the action score. So action score divided by n, which is the total tries. Oh, actually, it's not really total tries, because it's like more like action tries actually. Okay, so if you want to do like array Python element wise division. Okay, so we can do the np.divide function. So let's just call this as np.array. Actually, I could just call it as np.zeros, but I think this is fine. So np.divide array1, array2. NA outputs in the output array. Yeah, actually I don't need np dot divide. I could just do a divide like that. So this will divide whatever. Okay, so over here, because we cannot divide by 0, so by default we should put everything as 1 first. So the number of tries will be 1, which also means that we need to try out the moves like at least once. Yeah, okay, it doesn't matter because like later when we divide by 2 or divide by 3, it will work out in the end. So action score divided by action tries plus, so let's go back over here, plus a constant. So over here we call it C, and over here we just initialize C to be 1. Yeah, C, which is the exploration constant, times square root of ln ni over ni times np dot square root. Okay, ni ln ni over ni. So ln. So how do I do ln in Python? I think I will just do np dot log. Yeah, np dot log. Okay, I don't know whether this is a good function as of now. I'll just do it first. np dot log ln ni over ni. So we need to do this ln ni, which is np dot log. And this big Ni here represents the total number of simulations after I move run by parent node of the one considered, which also means that uh, yeah, the total number of simulations after Ni move. Yeah, okay, so this Ni actually is the number of tries for that node. This Ni is the total number of simulations. Okay, so this will grow bigger and bigger, but if your base is like not as high, okay, then there's a high chance this term will be quite big. Okay, so we could do like this. C times np dot. Okay, there's a small issue here. Like this thing here. The action score itself might be pretty large a number, and we probably might need to normalize it somehow. Because your action score over here could be like 30 over 1,000, and then this might overshadow this term here. Yeah. So maybe this C here, it could be pegged to the current board states. Like C could be pegged to the current board states score. Let me just try it. So because the C here will need to be dynamic and change according to like how big the left term is. You don't want the right term to be super underwhelming and the left term to overwhelm it. So let's just put like C is current state 1. And current state 1 is actually the same as the score of that state. So we peg the exploration constant to the initial action score. Sorry, to the initial board states that board state score. Yep. So that should be good. And then we do an explore exploit trade-off. So okay, so I realized this Ni is the number of simulations for the node. So number of wins for the node, number of simulations for the node, N is the total number of, yeah, so this N is like the number of tries for all the nodes, all the actions, and this small n is the number of tries for each action. So mp.log big N will be num tries, will be total tries, and then divided by the individual value here, which is the action tries. Let me just do some check. Okay, so if let's say I have a, if let's say I have like an array like that. Okay, so what this actually means is something like that. 80 divided by a. Yeah, it divides it well. So let's say if I have a b, maybe I do it like 2 5 3 4. So if let's say I do b divided by a or a divided by b, yeah, okay, so it works. So mp.array works. I wonder if it works for, can I undo it? No, I can't. So I wonder if it works for normal arrays. Let's say if I do like that, and maybe I have a 6 2 3, then I do b divided by a. Yeah, no, they don't allow. So only NumPy arrays allow that. So NumPy is a great library for Python. If you use Python, you should probably just use NumPy along with it, because it's too good not to use NumPy. Yeah. Okay, so what do I have here? So this one is the explore exploit trade-off. I think this should be correct already. So we need to find the max of this. So find max element position in array Python. So I believe it's like something like up max. Okay, so you just take the max and then dot index. Yeah. I wonder if there's a way to do it better. Yeah, I guess. Okay, so move equals to, okay, so I have again, this is best move, so actually this one we don't need this. So we add the score and tries to the action node. So what we do is we do action tries move index. Okay, so over here we have a move index. Move index equals to action heuristic dot index action heuristic dot, or rather max of this. Yeah, so we get the max element of this array, and then we get the index here. So over here we have a move, and the move will be up, down, left, right. Okay, so there will be some moves that will have uh, an extremely, like, if not valid, maybe we should have our action score to be a very negative result, so that we don't do that move at all, so that we will never do that move. So maybe we do it like that. We have a very negative score here, so else action score. Okay, so we probably need to convert this to, okay, so let's just do a dictionary to do this. Okay, index move to index to move equals to 0 is up, 1 is down, 2 is left, and 3 is right. And then move to index is the other way around. Down, one. That's what I like about Python. It's so easy to code it compared to other languages. Uh, okay, I mean after I use Python, everything else is a difficult language. Only Python is nice to use. So we have an index to move and move to index. So over here, uh, uh, actually I in order to avoid choosing, okay, actually I don't need to do this. I could just in this, actually I may not even need this tool here. From the thing of it, yeah, I could just in this action heuristic here, we can just avoid picking those stuff in the valid moves. So yeah, so we could do like this for, okay, it's not very Pythonic, but this one will get the job done for I in range 4. Okay, so over here, so we could have like the max value equals 0 or equals to -1, max index equals to -1 also. Okay, if max or if action heuristic, okay, if the action heuristic I, okay, is greater than max value, okay, then n, okay, I in valid moves. Okay, so over here, this I here is in up, down, left, right now. So we will need to convert this. Okay, I guess we will need this to after all. Let's just put it back and move to index I, or rather index to move I. We should convert our index to the move, index to move I. Okay, up, down, left, right in the valid moves itself. Okay, only then, okay, then we update our max value equals, so this will ensure that the action we choose is will always be the valid move. We are not going to waste time on and to do stuff that are not valid. Or actually I could just mask the action heuristic for the non-valid moves with a negative score. That will work as well. Yeah, but it's okay, I'll just do this. Yeah, I could do masking as well. Come to think of it, I don't need to do this, but since I already did it, let's just continue. One thing in life, you don't like regret doing what you do, you just move on. Okay, max index equals to I. Okay, that would be good. So move will be equals to index to move max index, and then we can do the Monte Carlo simulation, and then after that we could do like either the max index or the move. So over here, action tries max index. Okay, the max index plus equals to 1, and then the action score. What do we add here? For the action score, we add in the action heuris. No, we add in the Monte Carlo score. And we can print out everything. Okay, let's just see whether it works. Okay, so over here, move equals index to move max index. Key error -1. Oh, so this didn't work. Okay, maybe we should print out what is action heuristic. Nan. Okay, why is it a nan? Okay, action score divided by action tries. It should be a 0, right? So let's do some investigation work. Yeah, so it's 0. So it's probably this next part here. mp.log total tries. Oh, I see it now because the total tries is at 0. So maybe we should just do +1. Okay, now it works. Okay, now we can see that everything is prioritized to like this one here. Yeah, maybe I just print out action heuristic. each of them so I can see. Okay, so oh, there's no best move here. Okay, let's see how I did it earlier. So I did the best move with the best Monte Carlo score. So in this case, for like this kind of Monte Carlo research, the best move will be the node that is most visited. So over here, what we can do is best move is the most visited node because the most visited node means is the high most the node with the highest promise. That's why it's most visited. So what we could do is like this best move, or you could do like the highest average value. But let's just go with the most visited node. Best move equals to action tries dot list or dot index max action tries. Yeah, so we get the index here. All right, and then this will be the best move. And then we still need to do the okay, this is actually the best move index. So best move equals to what do we need to do here? We need to do an index to move. I don't quite like my code. It's too convoluted. Like here to be more Pythonic. You can easily do this 6 lines in 1 line in Python. Should I? But I think it's okay. Let's just see whether it works first. NumPy has no. Okay, then in this case we need to use this thing called np.where. Okay, np.where is basically to check which are the locations that yeah, check which of the locations are as array condition dot non-zero. So np.where will just tell us where are the arrays with this max action tries. So we just take the first element here, unhashable type np.np array. Let's just try action tries equals to max action tries. True false true false. So if we do an np.where, what do we get here? Array 0, and then we take out the 0. Take out the 0. Okay, so we need to do a double 0. Or actually, what people can do is dot flatten. Oops. np.flatten. Yeah, mp.rebel, and then we do 0. Okay, but anyway, it just shows that we need to have another 0 here. So maybe this, although this might be a little old school C++ way, is the most reliable. Like this kind of here, it abstracts a lot of what is being done. It may not work. Oh, okay. You can see that it's only choosing one action as of now, which just means that the reward function here and the explore exploit constraint is still giving 0 for all the terms, which is a little weird. So let's see why is this the case. So np dot square root. Let's just print out this also. C times square root of. Okay, so maybe in order to help visualize this better, so we could do like exploration. We could do like this. 0 0 0 0. So the exploration term is at 0 all the time. Kind of weird. Okay, and also the action heuristic, we need to do the action score divided by action tries. Okay, but as of now, it looks like it's increasing. Okay, no, actually, it is. So it's already giving the average. Okay, but why is this thing here not working out well? Why is this the exploration term at the right side not giving the right answer? Yeah, that is kind of unnerving here. Yeah, the right side here is supposed to give you the right answer. Rather, it should increase in terms of exploration as you do more and more moves. Okay, this is the UCB1 formula. There should be an increase on the right side here, which is not what we are seeing right now. So there's something that needs to be done here to increase this right side. And let me think about it. Let me think about it. Uh, np dot square root this one dot action tries. Okay, maybe I'll just print out the action tries here also. Print action tries. Yeah, I like to just do some debugging here. Okay, so let's print out this too. Action tries 3111, action score increase. Yeah, so the number of tries is indeed increasing as we run the simulation. Okay, we do have, but then we are just trying only the first action, which is kind of weird because we are supposed to try out like all the actions actually, not just the first action. We are supposed to try out the actions that will lead to a better state. So oh, is it because of this? Did my MP print total tries plus one? Total tries updated. Okay, total tries plus one is correct. Um, Now if I divide this with action tries, I divide this with action tries, my I should get a matrix. So if I divide this by action tries, I should get exploration. Okay, before the word exploration, this is my. Oh, okay. So this is the term here. 1, 2, 2, 2. So this thing here gives us 1, 2, 2, 2, which means that the yeah, that means this part here should be 2 already. So c times mp dot square root should give us the right thing already. Yeah, so it looks like it's working here. Okay, so which only leaves with one thing. It means that the C term here is a 0, which kind of makes sense because like the board state is ah okay. So we need to cap it at 1 because we don't want it to be 0. Okay, let's see. Yeah, so the 5 here is 6. The exploration term here is not going up fast enough to combat the the score. Okay, so Yeah, our term here is not moving fast enough to combat the gain in the score. So it turns out that it's only exploring the first move itself. It's not exploring the rest of the moves. So this is not something that we would like to happen to see happen. Okay. I mean, while we would like to, I mean, it's nice to keep exploring one action. It's not good if the action, all the other actions are not being explored. We just only explore one. I mean, this means that you will always do left all the time, and you can see. I mean, if we were to let this run to completion, okay, if we let this run to completion, you can see that this approach would not give a very good score because and it's taking pretty long to do also. Yeah, it's only moving left right now. So I guess the doing this max thing here, doing this max thing here is actually increasing runtime. Yeah, because it was much faster before. Okay, let's just do a even simplified one. Let's just do like 20 tries instead of 20 times 4. We should just do like 20 like that. And you can see that it's not exactly doing very well. I believe it is only like doing the only available move like left. It will probably lose pretty soon. Yeah, I don't think this will give a good result. Yeah, I don't think this is a good algorithm right now because I need to balance out the exploration term in this Monte Carlo tree. So this explore term needs to go up way faster. If not, it cannot combat whatever is over here on the left. Yeah, so you can see that this is a board reminiscent of a player who just keeps going left every available move, and then if cannot, then it tries another valid move. So this is not a good outcome. Yeah. Let me think about what else to do for here. One thing for sure is that we want need to let everyone lose a single try first. Okay, that's the first thing that we need to do. Okay, because if we let everyone do a single try, we can get a rough idea of what score each one could do. Or better still, we just let everyone do like maybe 5 tries first. So it's a hybrid. So we could do like a hybrid, let everyone do like 5 tries, like what this method does. This method everyone does 20 tries each. We could do like a portion of that number of tries. And then after that, then we can perform the Monte Carlo simulation here to get the moves after that. To prioritize certain nodes to explore even more to see what to see whether that node should be better. Okay, so yeah, that's all for now. I'll continue this later on. I have a meeting right now. And yeah, if you're interested, maybe in another hour, I'll be back again to try to code this Monte Carlo research with exploration and exploitation. So yeah, stay tuned and see ya.